Bernoulli's Principle. A small plastic ball can be made to float above a blowing jet of a fluid. Airplane wings and airfoils are designed in a particular shape. Smoke goes up the chimney. All these examples are comprehensible only when the principle worked out by Daniel Bernoulli is understood. Bernoulli's principle explains that where the velocity of the fluid is high, the pressure is low, and where the velocity is low, the pressure is high. Bernoulli's principle states that when a non-viscous, incompressible fluid flows steadily, the sum of the pressure energy, kinetic energy, and potential energy per unit volume of the fluid remains constant at all points in the path of the flow. Now we derive the equation of Bernoulli's principle. Let us consider a non-viscous and incompressible fluid flowing steadily in a tube. The area of cross-section of the end at point 1 is A1 and it is at a height h1 from the Earth's surface. The area of cross-section of the tube at point 2 is A2 and is situated at a height h2, h1 greater than h2. According to the equation of continuity, A1 V1 is equal to A2 V2. In a small time dt, the mass m of the fluid passing the point A is rho A1 V1 dt. If we assume the pressure at point 1 be P1, the work done by the fluid that enters the tube at that point is P1 A1 V1 dt, and this work is positive because the force and displacement are in the same direction. If pressure at 2 is P2, then the work done on the fluid of mass m is equal to rho A2 V2 dt. At that point is P2 A2 V2 dt, and it is negative as force and displacement are in opposite directions. Therefore, the work done on the fluid due to pressure difference Wp is equal to P1 A1 V1 dt minus P2 A2 V2 dt. Equation 1. The work done by the gravitational force on the fluid as the fluid flows from H1 to H2